Swayam Prabha. Digital India. Educated India.
Hello students, welcome to this lecture. In last few lectures we have been discussing the vibrational spectroscopy. In particular, so far we had focused on diatomic molecules where there was only 1 degree of freedom. So, therefore, the vibrational spectra was rather simple. In today's lecture, we will extend our discussion and go towards vibrational spectroscopy of polyatomic molecules. As you know, if I have a polyatomic system, suppose I have n number of atoms. So, there are 3 n minus 5 or 3 n minus 6 number of vibrational degrees of freedom, 5 for linear molecules and minus 6 for non-linear molecules. Now, we have to learn how to treat these 3 n minus 6 or 3 n minus 5 degrees of freedom simultaneously. This will be the topic that we will take up in today's class. The first thing to do that, we have to express now the potential energy of this molecule which has multiple degrees of freedom. Suppose let us say we say this is my potential energy I give as V. This V can be expressed in the following way. We say that okay, let us have a V naught which is the standard potential which does not depend on the degrees of freedom. So, thus all other potential energy of the molecule can be incorporated in this, and then we can expand this V in a series expansion where this is the 0th order term V is 0, and then I have the first order term where I goes from 1 to 3 n minus 5 or 3 n minus 6. We are keeping it 3 n minus 6 so that we would do it for non-linear molecules, but for linear molecules the extension is straightforward. So, what do I have here? So, I have the change of potential energy along all xi's. What are xi's? In one dimensional system, that means a diatomic system, we had only one coordinate, that was the bond distance. So, there was only one internal degree of freedom, but when you have a polyatomic molecule, we will have many internal degrees of freedom. So, this I goes from 1 to 3 n minus 6 and xi represents one of these internal coordinates plus the second order term and I can go on writing the say third order and fourth order terms as if I require. So, now I am providing, so for a polyatomic molecule, this is the general definition of the potential energy. Now, let us look at this term, the first term 0th order term. So, this is a scalar term, this does not depend on the internal coordinates of the molecule. So, we can have this can be treated as a constant, or we can very well make this 0, so that in case there is some constant potential energy, we can add that constant to our final solution. So, for the time being we make this as 0. When I look at the second term over here, this shows the coordinate derivative of the potential energy. So, this term and this gradient at the equilibrium. So, this 0 at the subscript suggests that this gradient I am calculating at the equilibrium geometry. So, I know at equilibrium geometry of a molecule there are no imbalanced force. So, there are the net force on each atom becomes 0. So, therefore, the potential energy gradient must become 0 at equilibrium geometry. So, this becomes 0, this term is 0. So, now looking at this term, which is the second derivative of the potential energy with respect to two coordinates simultaneously xi and xj. So, this one I call as kij. So, I can simplify this expression, the first two terms become 0, then my potential energy becomes simply ij kij xi xj, where xi and xj are two internal coordinates of my polyatomic molecule. Now, let us see what would have happened, what would happen if I extend this expression to a diatomic molecule. For a diatomic molecule, I have only one internal degree of freedom. So, therefore, I or j they become simply 1. So, therefore, for diatomic molecule this expression becomes half and I goes from 1 to 1, similarly j goes from 1 to 1. So, therefore, I have only one possible value of k and I call that k, and x I x j both are same. So, therefore, x square. So, this is V equals half k x square, the one dimensional harmonic potential that we are so familiar with. So, we see that for a polyatomic system the potential energy expression that we have written down is similar to the harmonic oscillator potential in one dimension that we consider. Where are the anharmonic term? So, anharmonic terms exist in these higher order terms that we are not writing down, because we are only keeping at the second order. If we take third and fourth order, then the anharmonic terms will start appearing. So, within harmonic approximation we can limit our discussion to this. Alright. So, this is about the potential energy. Let us find out what is the kinetic energy. The kinetic energy of this polyatomic system can be written as sum of, so the kinetic energy for 1 degree of freedom would be given as mi V I square. So, V I is the velocity. So, half m v square. So, since we are defining the coordinates, so therefore, let us express it in terms of the coordinates. So, here I goes from 1 to 3 n minus 6. So, here I am instead of writing the velocity, I am writing time derivative of coordinate, which is equal to the velocity. So, this dot on top of x is because I am taking dx by dt, the time derivative of the coordinate. So, this is the kinetic energy. Now, I would like to simplify this by writing down in a slightly different form, where I define this q I as the following way. So, q I is defined in this way. So, this square root of the mass, in this case this is the reduced mass corresponding to the ith internal coordinate, and x I represents that particular internal coordinate. So, this I have made a transfer of coordinate from the internal coordinate x I to this is something called mass weighted internal coordinate. So, these q i's are called mass weighted internal coordinates. Now, what is the advantage of this q I? We would see, we already see that the kinetic energy becomes somewhat simpler. Now, let us express this potential energy that we had here in terms of this new mass weighted coordinate instead of the regular internal coordinate. So, if I try to do this, you would realize that nothing much will change here, because I simply changed x I x j to q I q j. That is because the k I j, the force constants over here, they are with respect I obtain this force constant when I take derivative with respect to x I and x j. So, now I have to take derivative with respect to, so here k I j I am defining as d square v by d q I d q j at equilibrium geometry. So, therefore, since these q i's have already mass weighted and these q i's also have the same mass weighted. So, the mass terms will cancel out. So, I can simply write the expression either in internal coordinate or in the mass weighted internal coordinate. Now, the total energy in this case will become T plus V, and that would be half. So, this is time derivative of the mass weighted internal coordinate plus this is the kinetic energy, and the potential energy is now. You see the kinetic energy depends on only one internal coordinate, that is nice, but when I look at the potential energy, I see that the potential energy term depends on two internal coordinates I and j, and simultaneously. So, this is a problem because I have got many cross terms, and because of this cross terms I will not be able to solve this problem easily. So, therefore, I do a trick. What do I do? So, I know that I have got these 3n minus 5 number of mass weighted internal degrees of freedom. I take some linear combination of these qi's to form another set of 3n minus 6 number of degrees of freedom, but these capital Qi's, which are linear combination of small qi's, the mass weighted coordinates, but the advantage would be that I would take such a linear combination which will satisfy the following rule. So, where I would, if I write down, so the difference is that when I go from this small qi's, the mass weighted coordinate, to this capital Qi's, I would make such a linear combination of capital Qi such that this relation holds. What is the advantage here? The advantage here is that, as you can see, that like kinetic energy, the potential energy also forgive me. So, there is no more j over here, that is the whole point. So, just like kinetic energy, the potential energy also depends only on one coordinate at a time, and that is I. So, therefore, one coordinate is decoupled from the rest of the coordinates. So, I can write this energy for qi coordinate at a time, and then I would go for qj. So, therefore, the energy terms depend only on that particular coordinate. The coordinate system that satisfies this relation, that I can write the total energy as sum of the kinetic energy and the potential energy corresponding to that particular coordinate, this coordinate system is called as the normal coordinate or normal modes. So, just to remind you, we moved from one coordinate system to another coordinate system here. We started with defining internal coordinates xi's. So, this can be some bond angle or bond distance, like for example, in the diatomic case we took a bond distance. So, if you have polyatomic system, you can define this x as a bond distance or a bond angle or even a dihedral, and we converted this internal coordinate of the system from xi to the mass weighted internal coordinate system. So, by multiplying the reduced mass of that internal coordinates mi with this internal coordinate. So, I have got this mass weighted internal coordinate, and now from 3n minus 6 number of mass weighted coordinates, I am deriving a set of normal modes or normal coordinates such that the energy expression is satisfied, as I have shown here, that the energy of the system can be written down as the energy of sum of energy of different normal modes. So, this is what the normal mode does. Now, how to derive this normal mode? So, this is essentially I have to set we have to solve some linear algebra problem to get these normal mode coordinates from the internal coordinates. At least for small systems like triatomic systems, this can be done analytically, but for larger systems it requires more exhaustive calculations, but numerically in a computer one can do this in a straightforward manner. Now, we will continue our discussion as to see how we can put this information in quantum mechanical perspective, and then see how situation develops. Now, we are going to talk about the normal modes of vibration. One important thing that you remember, we realize that when I am expressing my system in terms of normal modes, the nice thing is that the total energy E becomes So, this relation holds good. So, therefore, I see that the energy is a full total energy is summation of several one dimensional energies. So, therefore, I can say that I can express the Hamiltonian, the total Hamiltonian for this polyatomic system as the summation of many Hamiltonians HI's, where HI is now the Hamiltonian for ith normal mode, and I can express. So, this is the total energy, kinetic energy and potential energy. Now, when I am writing the quantum mechanical operator corresponding to this, I will write the kinetic energy operator h bar square by 2. Normally, I have a mass term here, but I would not have this mass term over here, that is because already the q has mass weighted term. So, this is what a one dimensional Hamiltonian would look like for one normal mode q I. So, suppose if I want to look how this would appear for a diatomic system for which that means one dimensional problem, then you can see that q I would simply become capital Q I is simply equivalent to small q I, that is because I have only one degree of freedom. So, there is no non-trivial solution of linear combination. So, q I is capital Q I is q I is small q I, and small q I is mass weighted internal coordinate. So, therefore, you have this h square by 2 m divide d square by dx square plus half lambda, which is lambda I, which is actually the kappa that we discussed earlier, and q I is again your x. So, therefore, the expression that we have goes down to the one dimensional problem nicely. So, now we have expressed our total Hamiltonian as sum of several one dimensional Hamiltonian. The nice thing about this this proposition is that when the Hamiltonians are decoupled, that means that I can simply add one Hamiltonian to another Hamiltonian, that means the systems are the solutions are going to be decoupled. What does that mean? That means the total energy E is going to be sum of E i's, where E I is the energy of one dimensional one of these one dimensional problems corresponding to q I normal mode. What would be the energy? Since the Hamiltonian looks exactly like a harmonic oscillator problem Hamiltonian. So, therefore, the energies are also going to be the harmonic oscillator energy levels. So, I am writing down I h bar omega I V I plus half, where omega I is the vibrational frequency corresponding to ith normal mode, and V I is the vibrational quantum number corresponding to ith normal mode. So, where V I will go from like regular harmonic oscillator, it can go from 0, 1 to so on and so forth. What about the total wave function? When the Hamiltonians are written in this format, the energies become additive and the wave function can be written down as product of individual wave functions. So, in that in other words, the total wave function psi is given as the product of the wave function coming from one of these one dimensional problem. So, here what is psi V I? Psi V I is the solution of one of this harmonic oscillator problem, and we already know that for one dimensional harmonic oscillator problem we derived the solution, and it comes out as we can express this in terms of Hermite polynomial. So, we know the results of this. So, for example, just to expand it. So, I have psi V 1 as a function of q 1, psi V 2 as a function of q 2, psi V 3 as a function of q 3, and so on and so forth. So, depending on how many number of modes I have, I will have those many terms in this product, where q 1, q 2, q 3 represent the normal modes, V 1, V 2, V 3 represents the vibrational quantum number corresponding to that particular normal mode. So, let us take one example. Suppose consider a triatomic system and triatomic nonlinear system. So, n is 3. So, therefore, the number of degrees of freedom, since I said this is non-linear. So, 3n minus 6 becomes 3. So, therefore, I have 3 degrees of freedom. An example of this kind of system can be your well known water molecule. So, I have got 3 degrees of freedom. Let me call these degrees of freedom as q1, q2 and q3. So, what are the possible vibrational states? Since in each case the lowest possible vibrational level is 0. So, the ground state of this polyatomic state, the ground vibrational state is simply 0 0 0, where in all the normal modes the vibrational level is at the ground state. So, this is one state. Of course, I can construct the other states by simply exciting along the q3 mode by one quantum. So, therefore, I have 0 0 1, or I can have 0 1 0 or 1 0 0 or 1 1 1, I can have many. So, these are all different vibrational levels for this triatomic molecule. Now, let us consider one of this state. What would be the energy of this state? The total energy of this state, to define the energy we have this expression over here, and we need to define the vibrational frequency. Let me define the vibrational frequencies corresponding to this q1, q2, q3 mode as omega 1, omega 2 and omega 3. So, therefore, the total energy will become, and along the first mode q1 I have V is 0. So, therefore, the energy is going to be h bar omega 1, V is 0. So, 0 plus half is half. So, therefore, this gives me half h bar omega 1, and along q2 mode, since it is excited by one quantum. So, therefore, V I is 1. So, therefore, the energy becomes 3 half h bar omega 2, and in the third normal mode it is not excited, it is in the ground state. So, therefore, it is half h bar omega 3. So, depending on your omega 1, omega 2, omega 3, the energy of this state will change. Now, in that sense, what will be the energy of this 0 0 0 state? Because that will be the 0 point energy. So, the energy of 0 0 0 state, the ground state, will be simply half h bar omega 1 plus omega 2 plus omega 3. So, this would that would be the 0 point energy of this 3-dimensional harmonic oscillator. Now, let us write down what is the wave function for this state. So, 0 1 0. So, now when I write down the wave function, I know that I have to write down the wave function in a product manner. So, first write down the wave function corresponding to the normal mode 1. So, normal mode 1, it is not excited. So, it is in the 0 state. So, therefore, I write psi 0. Psi 0 along q1, and along q2 it is psi 1 q1, and along q3 it is psi 0, because it is in the ground state along q3. What do I mean by psi 0, psi 1 and psi 0 along q1, I am sorry, q1, q2, q3. What do I mean by this? If you remember, we had this harmonic oscillator problem and we obtained the solutions. So, when V equals 0, the wave function looked something like this. For V equals, so this was for V equals 0, this is for V equals 1, this is for V equals 2. This was for one dimensional harmonic oscillator. Now, when I say psi 0 at q1, so I would take the lowest eigenfunction of harmonic oscillator problem along q1 mode, and I will take the psi 1, that means this one second solution for q2 mode, and I will take the lowest solution for the q3 mode, and then I would product. So, you can imagine that there will be 3 different Hermite polynomials in this expression, and we will have 3 different e to the power minus q1 square by 2 or e to the power minus q2 square by 2. So, I would recommend that you write down the explicit form of this wave function, so that you get a clear understanding of this. So, this is how we write down the total energy and the total wave function for a polyatomic system when we express the degrees of freedom in terms of normal coordinates. The normal modes bring, just to remind you, the normal modes bring one beautiful property to picture, is that each mode can be now treated separately. So, when I can treat each mode separately, that means where I have 3n minus 6 degree of freedom becomes 3n minus 6 number of 1 degree freedom problem. So, therefore, the solution becomes somewhat simpler. All right. So, this is how we have this normal modes of vibration problem here. In this class, we just discussed different degrees of freedom. We started from the internal degree of freedom to mass weighted internal degree of freedom, and then we went to the normal modes, and we see that how we can write down the wave function and the energy of a multidimensional system by using normal mode description. We will continue our discussion in polyatomic molecules vibrational spectroscopy in the coming class. Thank you for your attention.